In the last episode, I showed you all the best practices for acoustic testing in Room EQ Wizard, the graphs that I use, and how to interpret the data that they show you. In this episode, I'm going to go into the design plan for acoustic treatment in the studio. I'll talk about the theory and the logic behind each one of the modules that I'll be building, as well as where they'll be located in the room and why. Let's get into it. We're going to start things off by taking a look at Thomas's room in SketchUp. SketchUp, if you haven't seen it before, is a CAD program. It's amazing for beginners because they have a free version that is just based in the web. And that's actually the one that I'm using today. So here is Thomas's room. This is looking at it from the rear wall entry hallway with the entrance door. And if we just spin it up and we look at it from the top down, then the orientation in the room is there's a window here, which Thomas is going to be facing out. His speakers are here, and the mix position is here. And if you didn't catch the previous episodes as to why I did that, normally we would orient the mix position facing one of the short walls, but there were a variety of reasons why that didn't make sense in this room. So the dimensions of the room, it is 13 feet wide, exactly. It is 7'11" deep. And then it has a sloped ceiling. So if we orient around to the side here and we take a look at it, this front edge is 7'7" and it slopes up at about a 10-degree slope, and the rear edge is 8'11". And this was one of the reasons why I oriented the room the way that I did, because if he was facing down towards the short wall, we wouldn't have had symmetry. And that is one of the huge priorities in a room, especially for mixing, is symmetry. And the other thing is this expansion ceiling, as it's called. If a ceiling slopes up, it's called an expansion ceiling. If a ceiling slopes down towards the back of the room, it's called a compression ceiling. And because this is an expansion ceiling, it acts actually as a waveguide. And it also means that the energy from the front of the room where the speakers are is going to be expanding into reduced acoustical impedance. And it also allows us to place taller, larger rear wall modules on the back wall versus if we'd done it the other way around. What I would call this is a small room, okay? The room volume is about 850 cubic feet. And small rooms are acoustically very challenging. They're the most challenging because your boundaries are very close, which means your reflected energy is very close and higher in energy. The sound is all contained in a smaller space. And you have less room for treatment, and it also restricts the type of treatment that you can do in a room. So this room, we're going to have three priorities for the treatment plan. One of them is low frequency control, because the bass is always the most difficult to control in a studio. But if you don't get your bass under control and it's stepping all over everything, it has a massive muddying and masking effect that impacts your perception of clarity. So you can be making decisions in your room that just do not translate to other spaces. So low frequency control is going to be a top priority. Next is sidewall or early reflection control, you could call that, primarily from the sidewalls, ceiling, floor. And you want those in check because if those are coming back to you, they are at a short delay from the direct signal, and those are going to cause comb filtering, and they can also cause masking, and they're within what you call the Haas fusion zone, so they begin to blur and combine with the direct signal. None of it's good. You want to control the reflected energy and create what you might call an RFZ, or a reflection-free zone, at the mix position. Then the final area of control is going to be decay rate control. So in the last episode, we talked, when we're looking at Room EQ Wizard, about how one of the priorities is evening out the rates of decay, because in an untreated room, they are different for different frequency ranges. And you have some frequencies that are decaying at 4 or 5 times the rate of decay of other frequencies, and it totally skews your psychoacoustic perception of the longer decaying frequencies, making you think that they're louder. And if you ended up applying, say, an EQ subtractively to that frequency, because that's what you would naturally do when mixing a song, if that frequency is jumping out at you and self-resonating and it's too loud, you're going to notch it out. But then that frequency was only there in a problematic amplitude in your room because of the acoustical problem in your room. And so when you go and listen to that song somewhere else that you don't have that same acoustical issue, then your song sounds completely hollow in that frequency range, and your mix doesn't translate, right? So that's one of our main accuracy goals in a room, is the rates of decay and also the frequency response, evening that out. So that is the room. Now let's talk about the game plan for treatment in the room. Basically, I'm going to load in as much broadband absorption as this room can take. And we of course are going to have several constraints. One constraint we have is the size of the room, right? And the amount of acoustic treatment that you need to treat bass frequencies is large, typically, but we can definitely make a substantial improvement. And part of that just is getting a lot of absorption into the room to begin to take some of that bass energy and control it. Now, the other limitation that we have is budget. So there's what I might do ideally, and then there's what we can do practically with the budget that we have. And I'm gonna kind of give Thomas the best bang for the buck with our custom fabricated modules that we'll be building, but I'm gonna leave an upgrade path available for the room and kind of think that out in advance so that down the road, when he has a bit more budget to put into the room to kind of tweak and create some further enhancements, we have that flexibility as well. So I mentioned that I'm going to be using broadband porous absorption. I'm going to use that as the only type of room treatment. Anybody who's studied acoustics a little bit will know that there's all kinds of other treatments that you hear about, right? There's diffusion, there's scattering slats, there's Helmholtz resonators, there are pressure-based treatments like VPRs and membrane diaphragmatic absorbers. There's all kinds of different acoustic treatment. However, I said, best bang for the buck. And the go-to in this room is going to be using porous absorption, and we're going to be doing that with large broadband absorbers. These are absorbers that are going to run floor to ceiling, and I'm going to use multiple layers of porous absorption. It can be something that you want to carefully consider is the type of porous absorption that you're using. Are you going to use all one density, or are you going to use multiple densities? I've had a decent amount of experience and a lot of test results by experimenting with different densities of porous absorption. And because I only have a certain amount of space I can take up in this room, I'm going to be using a multi-layered approach. And I've found that that outperforms using a single density of Rockwool, especially in terms of bass absorption coefficients. And I'm going to be using three products actually, two of them by Rockwool, and one of them is a light density fiberglass. So on some of the modules, I'm going to be using a material by Rockwool called Cavity Rock. It is a higher density semi-rigid bat that is 69 kilograms per meter cubed. Then I'm going to be using Rockwool Comfort Bat, which is a more standard insulation material that a lot of people use in studios. It's 32 kilograms per meter cubed. And then I'll be using a light density fiberglass that is, I'm in Canada, and we have a Canadian supplier that makes a light density fiberglass that is good for certain use cases in the studio. So with these broadband absorbers, one of the big questions that a lot of times people have is, do you air gap them from the wall? And I'm going to be using strategic air gaps on pretty much all of the modules. Now, one thing to ask yourself is, if you don't have the same budget restraints, is filling that air gap with something going to be better than leaving it open with air? And the answer is, it's better to fill the cavity, but with very light density. So in the tests that I've run and the modeling that I've done, it always works out better to have a light density fiberglass filling the airspace. But again, that just costs more money. There's more build and labor time involved. So in this case, we are going to use air gaps, and we're going to leave that space completely open due to the budget restraints. The other thing that people ask is, okay, why do you go to floor to ceiling? Why are you putting in so much treatment? Isn't that going to over-trap the room? And a lot of people see studios with those little 2-foot by 4-foot wall-mounted panels. And those just are not going to provide the amount of low frequency control. They'll be great for mid and high frequencies that are more easy to control. However, in this room, I already know low frequencies are going to be the biggest challenge in the room. And so area of coverage matters. So when you see people talking about bass traps and you see these little things in corners, yeah, they're going to make a bit of an improvement. Putting them in corners is a good place to start, but it's much better, especially with the rear wall, if you can cover it floor to ceiling, wall to wall. Those corner traps that just kind of straddle a corner, you might get 15%, 25% area of coverage on those, and then the rest of the wall is untreated. The top seam where the wall and the ceiling meet, the bottom seam where the floor and the back wall meet, and the sidewalls. All of those need coverage if you want the best performance. So we're going to be using these big floor-to-ceiling, wall-to-wall broadband panels, especially on the back end, with an air gap. Now, the reason I'm not using pressure-based treatments, which you might see, like vibrating diaphragmatic panel absorbers, is because those are tuned in such a way that it's very difficult to actually get the frequency that you want with those. They're typically high Q, meaning they have a very narrow bandwidth of absorption. And if you get that wrong, which is very easy to do because it's difficult to tune these things, then they have very low or almost negligible absorption outside of that particular frequency, okay? And I've had better results just using porous absorption. And porous absorption, the more that you add into the room, it's going to do something else that's really, really beneficial for your room. It is going to take those resonant peaks of the modes and it's going to drop them in amplitude. And at the same time, it's going to take the bandwidth of the mode and it's going to widen. So it's going to drop the peak, widen the bandwidth. Now, why is that good? Well, first of all, it means that the mode isn't jumping out as much at a high SPL, and it's going to even out your frequency response that way. You're not going to get these hot spots at certain frequencies in the room. But the other thing it's going to do is it's going to help your modes to group together. So the sides of the modes, those are called modal skirts. And when one skirt of one mode overlaps with another mode that is adjacent to it, then they're likely to mutually couple and resonate together. And the problem with these modes jumping out the bass department is when they resonate independently. Okay, so the reason why you see the frequency response oftentimes looking more even in the upper frequency ranges is because you have more modes that are closely spaced and they mutually couple. So the more absorption you add to the room, the more you widen the bandwidth of your modes, the more likely they are to couple with the modal skirts and resonate together, evening everything out, okay? So that is our game plan for the room. Let's take a look at the modules that we're going to design. To make it a little easier to see what we're looking at, I've just deleted the front wall of the room so we can look through it. And the very first thing that I'm going to do To make it a little easier to see what we're looking at, I've just deleted the front wall of the room so we can look through it. And the very first thing that I'm going to do is build and install these two large rear wall absorbers. So these are going to be a design that I've shown before on the YouTube channel. So if you are really keen to build these, I will drop a link to a video in the description below. And it shows you how you can DIY build hyper-professional, very effective modules just like these for only $243 US. I go through the complete build plans, all of the measurements, all of the tools that you need, and even including wrapping it with really nice professional acoustic fabric like in my studio. And that's one of the benefits of doing this for yourself, because when you buy prefabricated stuff, it is much more expensive, 2 to 3 times more expensive. And a lot of times you can't even buy stuff that's this size prefabricated because they can't ship it, because they can only ship stuff that's small and light enough. So oftentimes there are acoustical compromises when you buy this off-the-shelf prefabricated treatment. So I love these modules. They are primarily what my room has been made out of, and they are extremely effective. I can vouch for them with tons and tons of testing. Now, I said earlier that we're going to use a multi-layered approach. So that's going to improve our low frequency absorption coefficients. We are going to use a front layer of 2 inches of Rockwool cavity rock. And that's going to be followed by 3.5 inches of Rockwool Comfort Bat, which is a much more readily available standard material that you see in like Home Depot and stuff like that. Now that's going to be 5.5 inches of total depth, and that's because the frames that we're building this inside of are 1x lumber, so we're using all 1x6, and dimensionally 1x6 is actually 5.5 inches by 3/4 inches. Now we're also going to be using a air gap. So if we take a look at the model from the top down, you can see that there is an air gap. How big of an air gap do you use? Well, a lot of people have seen the quarter wavelength theory, right? Where you want the front of your absorber to be at the quarter of a wavelength if you want to absorb that wavelength. That's absolutely ridiculous. In a room like this, we're never going to do that. So we are going to place the absorber closer to the wall, and we're going to use an air gap, but we're using an air gap that is equal to the thickness of the module. So 5.5-inch module, 5.5-inch air gap. That means the modules are a total of 11 inches off of the back wall, and that is the absolute max we could eat up in this room without feeling like the acoustic treatment was impinging into the room volume too much. And that's going to be enough. And you can see we have the edge of the modules are snug against the sidewall, and that is going to increase, again, the base absorption because base will accumulate there at any of the room seams. And I much prefer using these types of modules, especially where low frequency control is such a big issue, than the little wall-mounted modules. So anytime you see somebody mounting a 2-foot by 4-foot little module and they put it on the wall, worst possible acoustical waste of time, because you need the module off the wall a little bit to be acoustically effective, because it is going to work based on velocity, not on pressure. And also those little 2-foot by 4-foot toy panels do not address where low frequencies and sound accumulate, which is at the seams. So the top seam between the rear wall and the ceiling, the bottom seam between the floor and the rear wall, and the sidewall rear wall seam, that's all where everything's going to accumulate. So treating your room seams first is a good idea. Also, acoustic treatment that is placed in the bottom half of the room is actually more effective than acoustic treatment placed in the top half of the room. So floor to ceiling coverage is going to be the way to go. And the other thing is total area of coverage. So you see a lot of people talking about studio design and they just put things in the corners and that's it. That's great. That's a good starting point. But if you just put these corner traps in, you might cover 15% or 25% of your rear wall. Well, guess what? The rest of it's reflective. And so we're going to go for as much area of coverage as possible. Okay. Now, if we spin the room again, you can see we were not able to put treatment on this side, this third of the room, call it, because there's the entry door. The door is one of the reasons why I oriented the room the way I did, because you can open the door and it's going to vent and let base energy escape. Huge advantage, just letting the energy out of the room. Now, the other thing is, this is not in the initial plan, but in the upgrade path for the room, we can build a module that will attach to the door that will give us some extra absorption. And then we can also build a small module that will either straddle that corner or just a square that'll fit in this corner, and that'll add some extra absorption. But due to budget and time constraints, we are leaving that area of the room untreated for now. Next up are the sidewall modules. And these are going to be put here to be able to catch and attenuate the sidewall reflections that are these early reflection zones, right? We used a mirror to be able to locate where the sound energy was going to be hitting the sidewalls, and we are going to locate these right smack in the middle of that. The design of these are basically the same as the rear wall absorbers. They are going to be 5.5 inches thick, a 2-inch layer of Rockwool cavity rock, followed by 3.5 inches of Rockwool comfort bat. They are going to have an air gap, just not as much as the rear wall, because they're not receiving the full frontal impact of the speaker's energy. So if we take a look, top down, you can see there's a little 2-inch air gap with these guys. Now, talking about the efficacy of these modules, I'm sure a lot of you will have seen this. This is the porous absorption calculator from acousticmodeling.com. And in here, I am able to input and model what these absorbers might look like. And so I am using the multi-layer absorber modeler to be able to estimate the acoustic performance of these modules. This is not going to be perfect. The module has inconsistencies in it. It's a rough estimate of where you might be at. Where am I getting these numbers from? I have another calculator and spreadsheet that is included with the download below the video. I give all my materials away that support the course. So how I'm modeling these absorbers out is because I have a known density to work off of, and I have a gas flow resistance. And that is what is required to plug into the acoustics modeling software, right? You need gas flow resistance. Now, manufacturers of insulation don't usually provide gas flow resistance, so you have to get it from another source, which I did. And so this first known density and gas flow resistance is for Rockwool Comfort Bat, which is 32 kilograms per meter cubed, and the gas flow resistivity, which is indicated in Pascal seconds meter squared, or in rails, I'm just going to call it rails because that's less of a mouthful, is 10,000. Okay, so if we go over here and we take a look at the modeling, you can see you type in, you give it porous absorption, yep, that's the layer, and then you give it a thickness in millimeters, and then you give it a number of rails, or Pascal seconds meter squared, and it's 10,000. All I have that for is Rockwool Comfort Bat. Well, what about the other Rockwool products that we might want to consider using? There's AFB, there's Safe and Sound, there's Rockboard, there is Cavity Rock, there's all this stuff. Because it's all one manufacturer with one fiber structure, and I have the densities, I've just input a formula to reverse engineer from the known density and gas flow resistivity of Comfort Bat to figure out what the likely GFR or gas flow resistivity of the other densities of Rockwool are. This isn't likely to work very accurately if you try and model fiberglass, though, for example, because fiberglass is a different material and a different fiber structure and a different manufacturer. So you can see here that here's where I've got the Rockwool Cavity Rock, and I've got this, and I'm modeling it from the density, and so the gas flow resistivity is about 21,500. So what I've done here is I've compared the estimated acoustical performance of this multi-layered module with just a single density, just using 5.5 inches thick of Rockwool Comfort Bat, and with an air gap behind of 5.5 inches. So if we go back over to our results, you can see the blue line is the Comfort Bat and the green line is the module that I'm looking at. And you might say, oh, well, the acoustic absorption coefficient is actually lower, and it is, but it also goes deeper. So we actually have significantly more base absorption down in the sub-range using the multi-layered module, and that is because using a higher density material thin on the front, followed by a lighter density material, in my experience, that always outperforms just a single density. So that's called graduated density, and it's known in acoustics that using a higher density material followed by a lighter density material should outperform in terms of base. Okay, so I'm willing to give up a little bit of kind of low, mid, or upper base range absorption coefficient in this room to gain the extra control over low frequencies. Okay? In this absorption scenario, I'm showing you the difference that running an air gap makes. So if we take a look at my parameters, in both cases, I'm using the Warp Academy multi-layered base absorber, the 5.5 inch one on the back wall, but on one of them I've included an air gap, and on the other one I have not. So there's no air gap on the top one, the blue line, and there is that 5.5 inch air gap on the green line. So now let's take a look, and we can see, look at that difference in low frequency absorption coefficient. Just that's a really significant difference. So air gapping in this case definitely gets us ahead. So now that we understand the design of the modules and the materials that we are using, let's take a look at the game plan for the rest of the room. So the next step is to provide some additional control in the front of the room where we have both of the corners open. So we are going to use these traps right here, and these are going to be made with a 2-inch layer of Rockwool Cavity Rock. So when I have only a small thickness to work with, 2 inches in this case, I'm going to use a higher density material. That is definitely going to perform better. If I have a lot of space to work with, I'll use a lot of low density material. Like in my control room on the back wall, we have like 3 feet of pink fluffy fiberglass with some Rockwool on the front, and that is able to attenuate bass down to 30 hertz. It's crazy in this room what you can do with porous absorption. So if anybody out there tries to tell you that porous absorption is not effective at controlling bass and sub-frequencies, I think they have just never tried to build a module or run any type of scientific testing themselves. I have the test results to prove it. You do not need fancy Helmholtz resonators. You do not need PSI AVAAs. You do not need a whole bunch of diffusion Not that diffusion is effective in the low frequencies anyways, but a lot of people think that treating a room is more complicated than it is. And actually, if you just come down to the basics, you can do an incredible amount of heavy lifting in your room and get really like near professional results just by using the stuff that I'm talking about here. I'm using a 2-inch thickness of Rockwool cavity rock in this case, and that's it. That's kind of all we could do. We were stretching our budget already, and I oriented these in 2-foot wide frames that are 87 inches tall. These ones are going to straddle the corner, and they're not even going in at exactly 45 because we didn't have the space to do that. So they're in at a 30-degree angle. But what that is going to do is it's going to create an airspace behind them, and that's going to increase the low frequency absorption. So we're just getting more treatment into the room, more absorption, and we're using these strategic air gaps wherever we can. Sweet. Now, the final piece of this equation is the ceiling cloud. Do not leave your ceiling untreated. The ceiling is going to create a direct reflection, a specular reflection back to your mix position. And in this case, the ceiling is sloped already, which is definitely to our advantage. It's going to act as a waveguide. It's going to reflect bass into the rear wall absorbers, but we definitely want to treat the ceiling. A couple things about the ceiling cloud. One is Thomas and I talked about it, and we wanted to actually spend a bit of time and a bit of budget here because we wanted the ceiling cloud to be a real feature piece, a real statement piece. Thomas's room has these really beautiful tongue and groove pine paneling on the ceilings, and I wanted to be able to accent that with a ceiling cloud. And I came up with a really nice ceiling cloud design that uses all wood joinery. There is no screws, no nails, no fasteners in the ceiling cloud. It's all done really beautifully with spline joints or dowel joints. It's 6 feet wide, 4 feet, so it's a pretty large cloud. And it is using individually wrapped modules so that you can see an exposed pine wood frame that's going to accent the ceiling. So we used all really nice pine lumber for the outside of the frame. You can see it all. And we individually wrapped these 2-foot by 4-foot modules to slot into 3 bays in the ceiling cloud. Now, what are those ones comprised of? So ceiling cloud, we did a little bit of a different design for the porous absorption. We did a front layer of 1.5 inches of Rockwool cavity rock. We had some of those bats laying around from one of Thomas's friends who runs a different studio. So we had that material for free, so 100% we're going to take that. Allowed us to build the cloud. And then behind that, we used 4 inches of light density fiberglass. So we used that combination of the harder front layer, thin, followed by light density fiberglass behind it. Each one of the bats is wrapped in acoustic fabric, and that is the design of the cloud. And then we're going to hang it on an angle that is as well going to kind of simulate what the ceiling is doing. We're going to cant the ceiling cloud up, and that will complete the treatment plan for the room. There's 2 final things I want to talk about before we wrap up. The first is diffusion. You'll notice that there is no diffusion in this room. A lot of studio builders, you'll see diffusion in their designs, but those rooms are different, okay? They're much larger. In my room, which is considered a medium-sized room, there is a lot of wood accenting, and that wood will break up and reflect some energy back into the room, which is nice. In a small room, it is entirely inappropriate to use diffusion. The walls, the boundaries are simply too close to you. And if a diffuser is within 10 feet of your listening position, you are really, really going to hear it. And it's going to actually cause a detrimental effect to accuracy in the room and causing reflections within that Haas fusion zone that are going to blur things. Also, another big mistaken thing in studio design is people think that diffusers are going to do something about the low end. They do not. A diffuser is a mid-range and bottom of the high range effective acoustic device, because think about things in terms of wavelengths, right? Bass wavelengths, really big. In order for some type of acoustic treatment to be very effective against a big frequency, it also needs to be big and deep. And so in this room, not only are they really expensive and time-consuming to build, wood is very expensive, they're just entirely inappropriate for this particular room. Now, one exception to that is if you're using something like a space coupler. And a space coupler is something that we could eventually include in the upgrade path for the room. These kind of grid square radiators that you see, you can hang them from the ceiling cloud, and they actually act as miniature waveguides. They change the direction of frequencies and they scatter sound in a pleasing way. They can actually make a room sound bigger than it is, and with the amount of absorption that's going on in this room, we may choose to include some space couplers in the future, suspended from the ceiling cloud. The other place we may use space couplers in this room that could be advantageous is in front of the front window. So sound is being captured by all the other acoustic treatment in the room, and so mostly we've left the front wall untreated. But if you have energy going towards the front wall, like from people in the room, then having those space couplers there, you can see through them, and they provide a bit of scattering on the front end. So the second point I want to talk about is the fact that I have left the front wall largely untreated. And you'll see in my room here, it has a completely reflective, hard plywood front wall backed with MDF. It's completely reflective. There's no treatment on the front wall at all. And in a lot of studios, you might see rooms by Northward Acoustics, they have actually the entire front walls made of glass. So how can they get away with that? I know a lot of you will have been told that you need to treat glass. Well, it's because the rest of the room is a hemi-anechoic chamber. It's filled with absorption. So all the energy firing out, the speakers see a different room than you as the engineer or a listener do. So if you have a room that is entirely trapped, like it's actually an anechoic chamber versus what this is, a hemi-anechoic chamber, then it makes people actually feel very uncomfortable, and it can make you not want to be in the room for a long period of time because we're used to getting acoustical cueing that gives our brain a sense of being in a physical space. And when all of the boundaries are absorptive, and you're not getting any reflected energy back to your auditory system, it can be really uncomfortable for people. So it's not going to cause acoustical problems in the room to have the front wall live because the speakers only see the absorption. But people in the room making little sounds, shuffling around or talking, that energy is going to get reflected off of the front wall and will provide that type of comfort and acoustical cueing in the room. Okay, I know that was a lot of information, but I wanted to show you the complete kind of thought process, the theory, acoustical theory applied in practice, how this actually shakes out, and to talk through the strategy for this room. In the next episode, we'll prep for building. I'm going to walk you through all the essential materials that I'll be using, as well as the tools you need to get the job done right. Stay tuned.